All right, good afternoon. My name is Michael Garcia. I'm the Chemistry Lab Coordinator for Texas A&M University Corpus Christi. I am also an adjunct instructor for Environmental Science and Chemistry. And what we have here today is we're going to do a little bit of hazard chemistry demo. And we're going to look at incompatibles and reactives. And so in order to do that, we're going to look at trichloro-S triazine trione, aka pool shock or HTH. And of course we have our own chemical label on here, and we're also going to be dealing with motor oil as our hydrocarbon. And in addition to that, we have a couple other reactions where we're going to be using hydrochloric acid, 12 molar, which is 37% concentration, with aluminum. And then we're also going to look at sodium hydroxide, 20 normal sodium hydroxide, with aluminum, and look at those particular incompatible reactions. Now this one right here might take a little bit, so when it starts going, we'll come back to it. But let's go ahead and do this right now. So I like to do this demonstration because these are common chemicals you can find at your home, and it doesn't have to be this. It could also be calcium hypochlorite, sodium hypochlorite, things of that nature. Anything that's got a strong oxidant capacity. And then of course your feed, your fuel stock, which in this case is motor oil, your long chain hydrocarbon and multi-branch hydrocarbon. So what I'm going to do now is I'm going to introduce a proportional amount of my motor oil with my HTH, or my pool shock. Now this is used motor oil, because I like to recycle whenever possible. And we're going to let that cook for a little bit. So as that's going, whenever it really starts kicking off, you'll see the reaction, and it should make a nice little cake, along with potential flame. So the next one here I like to do is aluminum and hydrochloric acid. And you have a metal, a relatively reactive metal, and you have a reducing acid. Now this could be considered an oxidizing metal, because it has more oxidizing capacity than the other metals that are on the left-hand side of the periodic table. Now what's going to happen here is we're going to create a little bit of a hydrogen gas and a lot of aluminum hydroxide. Now of course whenever I'm doing this, I'm wearing double gloves. We're doing this in a controlled environment with a vent hood. And you can notice we've got sorbents all around. We're ready for whatever comes towards us. And just for a little extra added fun, see the advancement of the flame due to the addition of the hydrogen gas in there. So there's a little bit of extra fire coming from there because of the hydrogen gas. Normally the match wouldn't burn quite so vigorously without it. So like I said, what we have here, the aluminum is reacting with the hydrochloric acid to create aluminum chloride, and we're also creating hydrogen gas as a result. I like to use this one because it's always important to know what your container is, what's your vessel, what is the proper container for this particular chemical. A lot of times you don't want to put acids and metal together because they generally don't mix well. They are reactive and incompatible with each other. And the case here, I remember a story from Kingsville, A&M Kingsville, where some researchers thought that they were putting hydrochloric acid that they had not used yet. They were storing it in they thought they were storing it in a stainless steel dewar, and it was not a stainless steel dewar. It was an aluminum dewar. And when they came back the very next Monday, there was a nice fog of hydrochloric acid vapor and hydrogen gas that they had accumulated in their lab, and it destroyed all their equipment and cost them tens of thousands of dollars to replace all that gear. So it's always important to know what container you're dealing with and make sure it's the proper container with the particular chemical. Now here we have some ready-made 20 molar sodium hydroxide. Now here, sodium hydroxide is a strong base, and we're going to see a similar reaction here with our aluminum, but it's not going to be quite as vigorous as the hydrochloric acid, but it will be a similar reaction. It will also generate hydrogen gas, and in this case will generate aluminum hydroxide instead of hydrochloric acid. This one I like to talk about again because you want to know your container. Not too long ago there was a vacuum truck that went to go pick up some spent caustic, and it was on 77, and by the time it got towards Robstown, the back of the vacuum truck suddenly fell off because his supervisor had told him to take this vacuum truck and go pick up the spent caustic, but the supervisor didn't realize that aluminum was the container. The vacuum truck container was made out of aluminum, and sodium hydroxide are not compatible. And so as a result, they lost the vacuum truck, or they lost the cargo in the vacuum truck. So this is a strong acid corrosive waste with a strong base caustic waste. And a little extra aluminum for fun. The gas being emitted again is hydrogen gas. Let it build up one more time. Now it's a candle. Now with your spent acids and spent bases, just because they're spent does not mean they are not viable or reactive. Good. Okay, so what we have here, we have a sodium dispersion in mineral oil. To prevent it from reacting with air, I went ahead and put a little bit of sodium on the plate. It still has some residual mineral oil. We're going to react it with nitric acid, so you have a strong reducing agent with a powerful oxidizing agent. And then we are also going to do potassium, which is also in mineral oil, in distilled water. And both of these are going to have a relatively strong oxidation reduction reaction. So the oxidizer is taking electrons and the reducer is donating them. Now we have here concentrated 70% nitric acid. I'm just going to use a little transfer pipette. And that is actually a toned down version of the reaction because of the mineral oil. The mineral oil is coating and preventing the oxidation process from going to completion suddenly. Now, we also have potassium, which is another strong reducing metal, even stronger. That's why I'm not combining it with nitric. Instead, I'm combining it with distilled water. And you're going to get a very similar, like I said, even stronger in this case, reaction with a beautiful purple flame. Now, needless to say, do not try that at home. So what we have here is copper shot. And what we're going to do is we're going to expose the copper shot. Copper is a strong reducing agent or reducing metal. Most of your metals are. And we are going to expose it to a strong oxidizer, also known as nitric acid. Now, what this does is it produces nitrogen dioxide gas, as well as a few others, and copper nitrate, copper 2 nitrate. So what's going on here, you're also, the green stuff down there is your copper nitrate solution that's being produced. It'll actually turn a blue when it's complete. Nice pretty blue. And then the stuff up here is the nitrogen dioxide gas. Now this is an acid gas. It is hazardous. It is deadly in high enough concentrations. You'll notice I have the sash all the way down and my face velocity is at 100, so I'm not terribly concerned about the gas coming into our breathing area. And that's why you want to do this in a well-ventilated area, because this particular reaction is not only is it exothermic, but it also produces acid gas. And those acid gases are not only deadly to you, but they're also corrosive to your skin and also your eyes. They will cause, the gas itself in a large enough concentration will cause permanent eye damage. So, like I said, very exothermic and relatively not good for you. Now, like I said, this is the motor oil and the pool shock. And as you can see, there's a great deal of gases liberated. Now, it's an incomplete combustion process, so you're getting not just carbon dioxide, but carbon monoxide, possibly some, you know, oil is not completely pure, so there's nitro groups and phosphorus groups, so you probably have phosgenes, some amines, other mixed chemicals in there, so it's not only a very vigorous reaction, although it takes a little while to get going, it is a reaction that liberates a lot of toxic gases, and as you can see, quite a bit of gas at the same time. So store your chemicals properly in your garage and in your home.